We're now looking at part 2 of our discussion of metric conversion problems using dimensional analysis as our problem-solving method. A quick reminder, in order to do metric conversion problems, you need to be very comfortable with table 2.1 in the textbook on base units of measurement. You also need to have memorized table 2.5 metric prefixes, and I'm specifically asking that you memorize all the metric prefixes starting with mega and going all the way down to nano. For example, the metric prefix kilo equals 1,000 or 10 to the third. You also need to have English to metric conversion factors memorized, and I've asked you to memorize these 3 specific metric conversion factors. There are others that can be memorized, but these ones are the most useful and most common to the units that we'll be working with here in Chem 2A. It's also very helpful to remember that 1 milliliter equals 1 cubic centimeter, and we'll talk a little bit more about that as we go through these additional problems. So we're looking at our 4th category of metric conversion problems involving metric conversions with units raised to an exponential power. And why would we need to consider that? Well, from your previous math training, you should be aware that if you're looking at a rectangle or a square and you want to know the volume of that rectangle or square, you can measure the length and the width and the height of that rectangle or square. And of course, those units would be units of meter. And then when you calculate volume, volume equals length times width times height. Dimensional analysis says that we have to mathematically operate on both numbers and their units. So meter times meter times meter, operating on the unit, would give us a cubic meter or cubic length. So it is very important that you recognize whenever you see a length unit raised to the power of 3, to the exponent of 3, cubic length is a volume, a measurement of the space occupied by that particular object. So here is our 4th example of metric conversions involving cubic length. And I'm asking you to convert 0.4 cubic meters into cubic centimeters. So we recognize we're not looking at length units anymore, we're looking at volume units. And I specifically asked you to convert to cubic centimeters because in healthcare this is a very common unit, except it's not written in the scientific form like this. It's not written with an exponent, it's just referred to as cc's. A unit of volume, referring to how much fluid is involved in this particular process, expressed as cc's or scientifically as cubic centimeters. And again, a cubic centimeter is equivalent to 1 milliliter. So we'll write that here. 1 centimeter cubed, or 1 cc, is equal to 1 milliliter. And this conversion factor, we could write that as a conversion factor, 1 cubic centimeter over 1 milliliter, would then enable us to go from cubic length to metric prefix of liter or any milliliter, deciliter variation of that. So a reminder to you, you should know 1 cubic centimeter is also equal to 1 milliliter. Memorize that factor as well. So let's go back to the calculation at hand. Erasing this, giving us space to do the problem solving. 0.4 cubic meters is equal to how many cubic centimeters? Our starting point, the data given, 0.4 cubic meters, and we need to get to cubic centimeters. I often see students approach this problem using the relationship that we've already discussed between meters and centimeters. So if I asked you, what's the relationship or a conversion factor between meters and centimeters? Meters is the bigger unit, the number 1 goes with that, prefix centi is hundredths, So 100 centimeters is equivalent to 1 meter. We've explored how to write that conversion factor. Here's the question we have to ask ourselves now. If this is a true relationship for length, can we also just cube each of those units and say now we have a true relationship for volume as well? In other words, is it valid? Is it true that 100 cubic centimeters is equal to 1 cubic meter? And the answer to that is no. This is not a valid, a factual, a true conversion factor. And if you use it in the setup, you will arrive at the incorrect answer. So what do? And this is where the beauty of dimensional analysis, in my opinion, really shines. So units are driving our setup. We have to operate on both the numbers and their units. So go back to what we just established. This is a valid conversion factor for length. 100 centimeters is equal to 1 meter. Well, what if I use that conversion factor 3 times? What if I write it out 3 times in this setup? And now what do I see for units in the denominator operating on the units as well as the numbers? Well, a meter times a meter times a meter is a cubic meter. We already established that. So if we have cubic meters in the denominator and we have cubic meters in the numerator here, then these units will cancel with each other. Looking at our numerator, centimeters times centimeters times centimeters, cubic centimeters, which is exactly what you've been asked to solve for. Bingo! Our setup is telling us, the dimensional analysis is telling us that we're done with this calculation. Now, before we finish it and write the answer, I just want to comment that I'm asked by students, why do we have to write it all out like that? That seems tedious and laborious. Can't we just take a shortcut like they taught us how to do in math and take 100 centimeters over 1 meter and just raise it to the power of 3? That certainly is a faster, more efficient way of writing out the setup than listing it all out 3 times as 3 separate conversion factors here. And I understand the point. Mathematically, this expression is equal to writing it out 3 times as we have done. I want to urge you to resist taking this shortcut when you're doing your setups for quizzes and exams. The A is in the details, and I've graded lots of papers, and what I've observed over the years is that students write this expression out, but in their nervousness, they forget to do the cubing. And their answer is incorrect because they did not do the complete mathematical operation. So I want to urge you, please resist taking this shortcut. You're much less likely to forget that you need to do 100 times 100 times 100 if you write it out like this. So I'm going to erase this form, valid, but not get it right every time approach to problem solving. So we'll go back to this setup that we have up on the board. Our units are cubic centimeters. Dimensional analysis says that the setup is complete, and now we need to do the operation and get our answer. I'd urge you to pause at this particular moment on the video. See if you can do this calculation, write the answer with the correct number of sig figs, and then we'll compare our answers. So I'm operating, you're operating, and we'll see what our answer is. I have actually double checked this, so I'm looking at the screen. I agree from repetition, this is the right answer. How many sig figs should our answer have? Our first Measurement of cubic length or volume has 2 sig figs. All of the other conversion factors, which are identical to each other, are exact. Within a metric unit, any conversion factor you write between one metric unit and another is exact, defined, no uncertainty, sig figs don't apply. So our answer should have 2 sig figs. My calculator is showing, and let's write it here, 400,000. Lots of zeros here. And a reminder that we're not sure whether those zeros are or are not significant if they're to the left of an implied decimal point. So if I want to write this answer with 2 sig figs to it, 2 sig figs, I'm going to have to put it in scientific notation, write in that decimal point, and move it to the left 5 spaces so that I have a single non-zero number followed by the decimal point. 1, 2, 3, 4, 5. Remember that any zeros to the right of the decimal point are significant. So this coefficient of 4.0 has 2 sig figs to it. I had to move the decimal place to the left 5 spaces, so that means I have 10 raised to the power of 5 as the rest of the expression in scientific notation, and I'm going to put my units of cubic centimeters at the end. Make sure not to forget to attach that unit. Numbers without a unit are almost always, to a chemist, meaningless. There's very few exceptions where we have numbers in chemistry that don't have units with them. Our last example is an example of a conversion problem where we're canceling units across a distance. And the example that I'd like to do for you is an example involving density. And we'll be discussing density later on in this chapter 2 that we are looking at right now on metric system and metric conversions. I chose as a density the density of a very well-known and precious element, highly valued, the density of gold. Density of gold is 19.3 grams per cubic centimeters. Density expressing units of mass in the numerator, and we recognize from our previous problem, volume in the denominator. So density refers to the mass occupied by a given volume of a substance, or if you have a certain mass of a substance, how much volume will it take up or occupy. When you see units that are written like this, numerator and denominator, but written horizontally, all on one line, it's important to remember that when you do the calculation, you can't write the units like that. You need to write them vertically, numerator, line, denominator in the bottom. And I started to write, and I'm immediately recognizing, I don't think I'm going to have enough room here, so I'm going to erase and move the problem a little bit further over to the left. So 19.3 grams per cubic centimeter, mass over volume, which is a density, the density of gold. And I have to convert that into units of pounds per cubic feet. Well, neither unit is what we wish to have in our final answer. We're going to have to convert them both. I, by default, almost always launch into doing the numerator conversion first. Doesn't matter. You can start by converting the denominator unit first to what you're desiring. I almost always tackle the numerator first, then the denominator. But doesn't matter which order. We'll see that. So I have a unit of grams, a mass in grams, and I want to convert to pounds. And here is our conversion factor between grams and pounds. So I am very quickly writing this conversion factor as the first step in the setup. 1 pound is equivalent to 453.6 grams. And I see immediately that my gram units cancel. So I've taken care of the numerator. I have the pound unit in the numerator, which is what I want. Problem is the units are now pounds over cubic centimeters, and I need to convert cubic centimeters into cubic feet. Well, I don't happen to know an equality between cubic centimeters and cubic feet. And based on our example that we did up above, I suspect that I'm going to have to use something that involves a length unit that I operate on 3 times. So here is our conversion factor between centimeters and inches. That's a length conversion, but if I write that length conversion 3 times, 2.54 centimeters over 1 inch times 2.54 centimeters over 1 inch times 2.54 centimeters over 1 inch, I see that I have been able to cancel out my cubic centimeter units, and I now have cubic inches for my unit in the denominator. So right now my setup's showing pounds over cubic inches. And let me comment before I go further, I am illustrating right now exactly this last category of metric conversions. I canceled across a distance, meaning I canceled cubic centimeters in the denominator with cubic centimeters in the numerator here, ignoring this conversion factor that's interrupting or coming between the conversion factors I'm working with. You can cancel a unit in the denominator with its corresponding unit in the numerator, even if they are separated by a distance or with other conversion factors separating them, coming between them. It is okay, valid mathematically, to cancel across a distance. And why is that true? Well, from previous math courses that you should have had, if you take A and multiply it by B times C, that is equal to C times A times B. In other words, you can scramble the order of the factors that you are multiplying and still maintain the equality. So we can scramble these conversion factors up if we would like and put this pounds over 453 grams at the end and have an adjacent flow of units. Canceling across the distance is the same as canceling adjacently. So that's what I'm illustrating in this last problem that I'm doing. Erasing what I have here, because I see we're not finished with the problem. Our denominator units are cubic inches, but we need to get to cubic feet. You should be familiar with the English to English relationship. 12 inches is equivalent to 1 foot. In healthcare here in the US, most people would give their height in feet and inches rather than in centimeters, which is commonly the unit of height in other countries. So here in America, feet, inches, very common, and you should know, you should memorize, if you haven't already, 12 inches is equivalent to 1 foot. So I'm going to take that equivalency and write it as a conversion factor. 12 inches over 1 foot times 12 inches over 1 foot times 12 inches over 1 foot. And I see that I have now enabled myself to cancel cubic inches in the denominator with cubic inches in the numerator. And my unit in the denominator is now cubic feet, exactly what I'm asked to solve for. So the only units left showing in the problem, pounds per cubic feet, exactly what we've been asked to solve for. So even though it's a lengthy setup, we're not confused. The dimensional analysis is telling us exactly what we've done here. The only thing left to do is operate on the numbers in the setup and express our final answer with the correct sig figs and the correct units. So I'm inviting you to pause this video, while you do the calculation yourself and express your answer and compare it with the answer that I have calculated. And I've already double checked this, so I'm not going to take the time right now to do that. And here's what my calculator showed when I operated on this. It gave me an expression or a value of 1204.8. And of course the units are pounds per cubic feet, but we'll write that in later. So that's what the calculator is showing, but how many sig figs should our answer have? This first density is a measured value with 3 sig figs. Our mass conversion factor, English to metric, is not exact and has 4 sig figs. This next conversion factor between centimeters and inches is unusual in that it is exact. Most English to metric conversion factors are not. Sig figs do not apply to them. And then English to English units or conversion factors between English to English units are exact, just like with metric to metric units, sig figs don't apply. According to rules of multiplication and division, for significant figures, our answer can have no more than the smallest number of sig figs used in the setup, which is 3 sig figs. So I have to express this answer with 3 sig figs. Uncertainty is in the tens place. What comes after that 0 is less than exactly 500. So I will not round that 0 up to 1. I will leave it as 0. I'm going to have to put it into scientific notation in order to express it properly with 3 sig figs. Moving that decimal place to the left 3 spaces, I have 1.20 times 10 to the third pounds per cubic feet. 1.20 times 10 to the third pounds per cubic feet, which is a large number, but when you think about a block of gold that measures a foot by a foot by a foot, that's going to be quite a mass of gold. So 1.20 times 10 to the third pounds per cubic feet is the density of gold expressed with 3 sig figs.